So I love these regional partnership models. I don't know, starting 3 years ago, I spent about a year and a half of my life that I'd like to have back, stitching together a hydrogen hub effort between Colorado, Wyoming, Utah, and New Mexico. We've started off with Colorado, we've had Utah, and coming up next, we have New Mexico. So my pleasure to introduce Thomas Hauser, who's the Associate Director of Computational Information Systems Laboratory at NCAR, the National Center for Atmospheric Research. And in that role, he's responsible for state-of-the-art computing, data analysis, visualizing services, supporting the Earth System Science community. We had a brief chat on the energy uses at the facility, and so I'm looking forward to hearing what they're doing and what their plans are moving forward.
Seems to work. Yeah, thanks for the invitation to be here. I mean, I started actually my HPC career building a small center at Utah State in 2005, and then I went to Northwestern. I never thought I was going to be at NCAR leading the Center for Computational Information Systems. So that's my current job. I've been there in this job for a year and a half. And a lot of these ideas I passionately care about: energy efficiency, data sharing, democratization. So I think this is really a great opportunity to talk more and figuring out maybe how we work together. So we are a little bit differently funded than most of the national cyber infrastructure. We do fundamental research at NCAR on Earth system science to address, extreme events, climate change. And we are funded out of the Geo Directorate, so we are a little bit disconnected, and one of my goals is to really connect NCAR much more into the national cyber infrastructure ecosystem there. We support the scientific community. We have world-class models. I don't know who's an Earth system scientist, but we have WRF, we have CSM, we have MPAS for weather forecasting. We have all kinds of models. Then we provide HPC and data services to the community. That's mainly my lab. We also do a lot of software engineering and visualization. And then we have planes and instruments to do campaigns, measuring environment. And then we do a lot of training, and we have also opportunities for students and postdocs to come to NCAR. My lab, Sizzle, supports Earth system science. First of all, through our computational data infrastructure, and I go a little bit more into detail there. The other piece is really easy access to data. I have a big initiative that I started to really democratize data. We had a lot of silos at NCAR before I came, and I'm really trying to integrate this, bring this together, kind of trying to implement a concept of a data commons, and then connect into the national infrastructure, kind of the NSDF and Pelican. We are working on that as well. So we want to really make sure we can deliver the data to the scientists in the format they need it. So that's one of our goals there, and make it easy to do. We have a lot of tools, models, analysis, visualization, and we are starting to develop AI tools and AI workflows there. I think data assimilation is something that's maybe more to the weather and climate. I'm not a climate scientist. I learned about this. This is kind of specialized. How do we initialize our climate and weather models? And then on the machine learning side, I have a small AI research team, and we are kind of beefing this up to really try to provide a community AI ecosystem, so where we integrated data, the models, and make it easier to use. One of the things I really liked when Penny mentioned translational computational computer science. So this is an area I really want to bring in. This is an area we are at the moment weak in my lab, but I really want to grow this area, bring computer science in and apply it to our Earth system science problems. I was really happy to hear that. A little bit about Sizzle by the numbers. We have about over 2,000 HPC users from 364 institutions. A lot of growth in the kind of more on the lower end. initially, our access is restricted to geoscience or earth science funded, but we open it up. So if you need to analyze and use our data sets, you can get access to our data analysis infrastructure. So we open it up more widely there. We do deliver a lot of compute hours. I mean, again, I mentioned the PoE. I'm pretty proud about our facility. It's very energy efficient up there in Wyoming. So it's in Cheyenne. So it's not at my main office is in Boulder in the Mesa lab, but my computer system and about 20 of my staff are in Cheyenne there. We actually close to sign contracts to be carbon neutral, which now with this current administration, I'm going to fly under the radar with that. I'm very proud of it, but I don't want to steer things up in that space. So we have a lot of users of our data. I think that's key, and I think we want to build that out there. And we're living about 23 petabyte. There was something on disaster recovery you mentioned. So we have a data archive, we are a trusted repository. One thing we didn't think about, what happens if NSF shuts us down? So I'm actually working on I hope it's not going to happen, but I'm working on a kind of a disaster recovery strategy, kind of nationally and internationally, to kind of make sure the data sets that are unique for NCAR. I can mine Bitcoin too, yes. We actually had a Chinese Bitcoin mining operation right across the street that was forced to sell because of the missile, the Air Force base in Cheyenne, so there was some national security implication of that. Again, we deliver a lot of our compute hours to the community, so we have NCAR internal, we develop our models, so we use quite a bit, but about 37% go to the university community. We also, the University of Wyoming is a partner in our systems. We do one thing that actually is operational. We are really a research organization, so we don't do operational. But the one thing we do is actually deliver the daily forecast for Antarctica, the station from NSF. So we do one thing that's operational. And if our system is down, we move that into the cloud. And as you can see, we already have a portion of our system is GPUs. So we support some AI, ML workflows as well there. This shows a little bit our infrastructure. We have our flagship system, the Retro. It's kind of the main HPC system, but then we have a large storage infrastructure from kind of different tiers, kind of speed. We are trying to move more towards tape. We get more and more data, and I'm moving towards more really exascale on the data side. But a lot of our data also is not very often used. So I'm trying to tier our data so that we go to more energy efficient. Tape is kind of very energy efficient. It's slow, but I think so we're trying to create an architecture where we kind of tier our data. And then we have our data analysis cluster. And recently we are deploying a kind of a cloud system, and we'll merge that with our analysis cluster. So we can use cloud technologies, Kubernetes, containers on our system there, and develop data portals, so we're democratizing access to our system. This is kind of a little bit of the technical details about our system. It's about a 20 petaflop system, 60 petabyte of at scratch, so lots of data. We run, kind of starting to run high resolution climate simulation, need a lot of I/O capability, and I think our newest thing is AI. Some of our AI workflows can easily flood our bandwidth, so we have to do something in that space because of the data, that bandwidth that's needed. We deliver about still 80% of our performance through CPUs, and then 20% is GPUs. And then we have our really fast, or relatively fast scratch file system. Everything is liquid cooled. We have about 6 megawatts of power use up there. Most of it is not backed up. You mentioned at the beginning, we have some generators and we have a UPS, more for our storage and for the systems that need to run up. So if the power goes out, we don't run into trouble with our storage and infrastructure, and can shut everything down kind of in a controlled manner. One of our big things is our modeling environment. We have kind of a variety of models. We have a solar physics called MURAM. We We have space weather with Welcome X. We have CSM, our flagship climate model. We have MPOS for weather, and then we have different land, sea ice models there. So we have a kind of, and then chemistry, atmospheric chemistry. So we have a variety of different models from really local scale, LES, to kind of global scale, to really study kind of our Earth system. We're making a big push to improve our Earth system models with AI. So we are really trying to integrate high-resolution kilometer scale, really expensive simulation with high-resolution observation, creating some models. And again, there's a lot of, this is still hard work, creating some of these parameterizations for the subgrid scale physics effects using AI, and then improving our modeling and prediction capabilities with machine learning. Then again, with AI, we may want to do some regional downscaling. And then our vision is also, how do we bring in other effects like health or population data, and kind of create a digital twin for decision makers in kind of in a research environment. So we're still, but this is kind of plans in the future. We're working on that. I'm doing a workshop with some colleagues in Italy, kind of talking about these, what's our roadmap in this space. And again, the foundation for this is a modernized computing and data infrastructure and high resolution models. We have really kind of different needs, so it's kind of hard for us to where do we go in terms of computing. We want to do high resolution global. So these are actually workloads that would fit nicely on GPUs. But then a lot of science can still be done with low resolution, lots of ensembles to do uncertainty quantification. So this is more CPU, and then increased complexity, right? How do we add more chemistry, more other effects there? So we kind of have a broad spectrum of different needs, and we need to find the right system in the future. And I think that's kind of the big question mark for us. Planning for the next system. This current system was deployed about 2 years ago. The next one comes in 3 years, so we're starting to kind of design the next system. We're also working closely, I mean, this is maybe an opportunity here in the region with the Colorado-Wyoming climate engine. One of the deliverables my team had to do is designing, or at least doing a study of the feasibility of what would it take to create a data center and host a 30 megawatt system. So a pretty large system, and that might be actually something to think about. What can we do regionally here? How would that look like? Can we bring in, especially with this new administration, some industry, do this in a very energy efficient way, but really provide capabilities for our research community. One of the things is I'm shifting focus in my team a little bit, and I make a pretty strong statement here. AI is HPC. I think AI and HPC infrastructure are converging. If you look at what the commercial cloud is doing in recent years, because of these large language models, they are deploying high-speed interconnects, InfiniBand. I mean, Microsoft deployed thousands and thousands of kilometers of InfiniBand in the data center, because now for these training workloads, they need low latency, high bandwidth interconnect. It's very different before MLs, right? Cloud infrastructure, HPC infrastructure was different. I mean, it was loosely coupled. They do much more higher performance I/O, and then scalable software. They're using MPI now that they haven't used before. And so I think this is an opportunity for us. I mean, we are experts in HPC to engage with those. It's also a threat for me a little bit. I feel like my system staff may be lured away by the high salaries of kind of the commercial world. So our expertise, I feel, that matches actually very well with the expertise AI needs. It's a different application, different characteristic. And then I think I was really happy to hear kind of energy efficiency here. I mean, I think there's a lot of work to be done on efficiency, AI, energy efficiency. I think the current path for me is not sustainable. I mean, financially and I mean that climate-wise. I mean, I think we just we can't just bring in more and more data centers. So energy efficient, algorithmic. What can we do in AI to really reduce the energy footprint and not just go kind of brute force, bigger and bigger? So it's a big effort. I actually have a nice, and I'm very interested in other collaboration. I have a collaboration with the University of Edinburgh, with the Edinburgh Parallel Computing Center, and we have a center-to-center research project looking at energy efficiency, really from the data center to our HPC system to our codes. And one of the things we are also focusing is data movement, because moving data can't, compute architectures is more expensive than doing the flops. So I think I was very happy to hear that. The other one is, I think, the challenge for kind of my traditional modeling colleagues is, I mean, all the investments will go in AI hardware. So how do we make sure our modeling codes run fairly efficiently on the AI hardware? The floating point kind of 64-bit floating point performance is really kind of flattening out. So what can we do? Can we go to 32 bits? Can we do mixed precision? What can we do to leverage kind of the trends in this space? So again, I'm working on a roadmap for our what I call NSF NCAR community AI ecosystem. I really want to make this easy to use, have kind of a model zoo so people can download the models, have the data there, have reproducible data workflows there. One area I'm also excited, I'm working with a researcher, and she is looking into fit for use. A lot of these data sets are just used by AI researchers, and sometimes they are really not the right data sets to answer that question or to create that model. So how do we integrate that into the metadata of our data sets? So this is an area we are kind of starting to do some more research and development work there. Ideally, from my perspective, I hope we can get an AI system in between before we have our next system, just to have a more AI-focused system there and learn. I think there's a lot of work to be done on the software and tools to make it easier to use. In my world, right, there's already quite a bit of a different set of weather models. But then talking to our researchers that use my supercomputing, it's like, oh, I need to use this Python version and then this other Python version to get it to run. So I'm working with them to make it easier to use there. And then developing new models, kind of AI models, forecasting. Because, I mean, I just was this morning at Sierra in an AI workshop, and it's really encouraging to hear that with some of these inference pre-trained models, you can do really cool science, and you don't need this high computational infrastructure. Inference is much more, it's much less expensive there. And then again, I think there's some talk, how do we train the next generation? What do we do on workforce development and education and training? We have in my lab an internship program. I like to grow this. I like to, again, collaborate on how do we move this forward. This is a little bit more on the traditional modeling side. So my teams are generally looking at how do we make these models run more efficiently on our supercomputers. And we have a few success stories with our Cloud Model 1 and Myram, our solar physics. And this is also kind of how we communicate. We always, before I came, I think we told them, yeah, you need to move to GPUs. But then our scientists perspective, why? And why do you make us do that? That was kind of the general answer. And now we actually give them the answer here. This is kind of the energy savings. And we put it in, since most of our scientists are climate scientists, we put it into tons of CO2 saved. And that really helps us to kind of start this conversation and having this engagement to move these codes to GPUs. And I think this is really, for me, kind of how, again, you need to find the right hook, how to engage them. And I think, again, this ties into energy efficiency by moving some of these codes to GPU. And it's the same thing for our Cloud Model 1, kind of similar. You can see the substantial savings in terms of CO2 for those models. Yeah, so one of my new focus is really trying to figure out how do we democratize AI. And I think at the core, we have data. I mean, NCAR really has a lot of, we have hundreds of petabytes of data. So we have a good foundation for that. And then at the same time, sometimes the data sits, and I think from Penny, your talk, right, it sits not quite where the computing is. It's hard to access. It's often not well described. So we are really trying to create a more modern data infrastructure, integrate this, and create federated catalogs so you can get to the data from our supercomputer, from others, but also integrate into the OSDF, Pelican. So we are trying to work that. And it's really exciting. I mean, I talked today with somebody from Sierra, and she's leading a South America affinity group, and they can't afford some of the infrastructure. I mean, and I think one step is we let them on our infrastructure on the data analysis side, but the other step could be they have some compute capabilities, but using OSDF, others to really make our large data sets accessible at those centers in South America. So it's really exciting there. We're working more on how do we create data pipelines, how do we make these data pipelines reproducible, and then there's a lot of tuning still necessary for some of these tools, because by default, I mean, our researchers come in, they do pip install and whatever model, and then they don't install the right libraries, and there's a large potential for improvement if you install the right version. So we're really working, making sure our users use our supercomputer as efficient as possible. And then I think there's this opportunity on the domain science side, kind of integrating the different domains, weather, climate, but also other effects that may be more difficult to describe with equations, like evocation behavior, things like that. What happens if there's a fire? How do this fire model interact kind of with a population model, kind of evocation model? So we're working on the kind of this interdisciplinary approach in this space. But we are just at the beginning, working with the community, working internationally, kind of on a roadmap. What's the roadmap for NCAR in this space? And again, this is when I came to NCAR. I mean, I was at CU before. I created the Center for Research Data and Digital Scholarship. So data is it's a passion for me, and it's kind of I would say, not very thankful work often. I mean, I like this idea, right? Publishing the data, because that's the currency. We're moving towards that at NCAR too. I mean, we're giving out DOIs, but getting credit for publishing a data set, that's still a little bit of a challenge in this space. So we really have a big project in my team and with other labs. So I'm working with our observational lab, with our solar physics lab, to bring all data together and then deliver the data. There's a lot of discussion about what format and which thing, and we should provide maybe APIs and abstractions, so we deliver the data in the format the researcher needs, and not just they need to provide another data translator there. We're also trying to expand our data management services. I mean, we have a pretty robust team and we do kind of data curation, metadata management. We'd like to expand it to our geo community at NSF. We're deploying some cloud services, so I want to really integrate kind of cloud technologies in our data analysis, AI, and visualization approach. And then we're looking at how can maybe large language models help with data management. I don't know. I mean, I think there's some work done there. We're also looking in this kind of fit for purpose, kind of how do we annotate our data to make sure this data, we probably can't prevent it, but the data is maybe not used in situation where it's not in the right. And it's kind of this picture on the right is really kind of trying to kind of sketching out how we look at our data platform for this. And then again, with AI, having a curated AI model so you can download, we're working on creating a Hugging Face space there so that we can deploy the models and our users can just download the models. We see an increase in our use, so we're getting more tickets. I'm actually surprised that there are not more tickets, so I'm trying to figure out why are we not getting more and more requests to help, because that's still pretty minimal compared to our super popular models like WRF. Like we did thousands of tickets about WRF and get kind of fairly limited. So I'm trying to figure out why that is. Maybe it's the data and the difficulties running these AI models. So this is one area. We are looking at why is this happening in this space. Again, I think performance is a big issue. You can see, I mean, depending on which library, how you install it, you get pretty big improvement in performance, and we want to make sure it's easy, it's kind of transparent for users. They don't really care about. And then on the data analysis side, we are really working on kind of LLM-assisted data analysis. So there's some work, we're collaborating with Stuttgart, with Hamburg. There's the DICA, the German Climate Computing Center. And it's basically, it's kind of hard to see, unfortunately, but it's basically you enter your questions. What's the land use in this area? And it gives you, you can actually draw on the map and saying, oh, this area I want to, the land use change, for instance, in this area. And then the LLM gets to the right data set, creates a plot, tests that the plot is working, because I mean, LLMs can hallucinate very confident and give you the wrong. But we're exploring some of these tools there to make Earth system science and data analysis much more easily. We also have kind of our own research platform. So we have CREDIT, the Community Research Earth Digital Intelligence Twin. It's really a research platform for my research team, and they're close collaborators at the moment. I think they have ambitions that this becomes a platform for the community, and I support that. But at the moment, to be realistic, I mean, it's them plus a few close collaborators, because it's still not that easy to use. But I'm actually doing a little bit of a reorganizing my lab to support that and really move towards a community AI platform. So you can do your own training there. I'm still looking at training is kind of I look at this as a pyramid. Training new models is probably a small user community. I see inference and using models that exist and maybe some transfer learning or some tuning more on kind of the main use. And I think that also is the question, how do I change my operating model, right? From maybe batch to more interactive, because you don't want to wait when you want to do inference, right? You want that more or less instantaneously. So that's a kind of a change in how we do computing in this space. And I just want to mention at the end here, so we have an internship program, so if there's students in this space, they can come to NCAR. We're gonna start in May, kind of our next cohort. It's undergrad and graduate, and it's actually not Earth system scientists, so we really try to attract other disciplines and work on Earth system science problems. So computer science, mechanical, electrical engineering, applied math. We provide travel, housing, 11 weeks of salaries, conference travel, so we generally encourage them to go to a conference. After that, could be supercomputing, but they can have their choice there. And it's pretty competitive. At the moment, we do 10 to 15. I'm trying to figure out how do I scale this up. So again, this is a really good opportunity. And to end, I think our challenges are not unique. So I'm very open to collaboration and pursue partnerships, especially here in the region. So I was really happy to hear some of these things that I'm passionate about: energy efficiency, the data sharing, democratization of AI. So very interested in having more conversation on how do we work together. And with that, ready for a question. And these are kind of my team leads. So I have different teams that contributed to these slides. So thank you.
Thank you, Thomas. And I'm going to use moderator's privilege to ask a couple of questions. First, I'm just really stunned by the carbon implications of switching to GPUs, of 10x, going from 51 tons to 4 tons and going from 72 to 14 tons. So I guess my question is, from the, what I've been seeing are the projections from the energy side, looking at how much transmission do we need to put in, how much gas we're going to use, how many turbines. I'm really interested in your thoughts. Do we become more efficient, and that energy growth declines, or do we become more efficient? And what we've seen in other areas, what we saw in transportation, is vehicles became more efficient. then we just had more vehicle miles traveled. So do we get more efficient and just do more computations, or instead of this 60% energy growth, is the opportunity to get more efficient and that number comes down?
I hope for the latter. I mean,
We hope for. Are you guys thinking, I mean, from the computational side, what the implications are? And I don't really have a good idea whether those projections are code-developed or if they're just extrapolating current numbers.
I think from my perspective, and I haven't totally researched that, I think they are protecting the current numbers with the brute force approach. And I think there are opportunities in AI to do more energy efficient things. But the question is, do we then just do more AI? And I don't really have a good answer at the moment about that, right? So.
Okay. And the second was, I was really pleased to hear you mention the Colorado-Wyoming climate engine. So this is one of the research innovation engines funded by the National Science Foundation. It's got 40 different partners. It was really led by, the lead on it is Innosphere Ventures, which is here in Fort Collins, and is really, CSU and Innosphere really spearheaded this, but it's got really strong partnerships all throughout Colorado and Wyoming. And it basically uses advanced sensing and computation to support new resiliency around air, water, fire, and soils. So I'm curious what activities you are taking place and you project will take place as part of the climate resilience engine.
Yeah. So we hosted, I think, the first digital twin kickoff for the startup. So there's a kind of a startup ecosystem. I think they want to create a startup. So I think that's interesting. I'm still trying to figure out where we fit in. I think we can provide some expertise in a lot of the earth science that we have. It's a little challenging for us to engage. We can't receive funding from that engine. So for me, there's definitely an opportunity to do more and provide the expertise in computing, and we think about new models. How do we engage? So I don't have final answers. I mean, this is pretty new, right? This started a year ago. We contributed this. I think they want more advanced computing, and that's why I did this 30 megawatt data center kind of study. How we leverage that, I think that's a good question. Maybe this is something we should talk as the institutions in the region and the engine, and kind of what's the path forward to how would they leverage some of these advanced computing approaches in that space. So.
Okay, so I'm going to stop monopolizing and ask if there are other questions for Thomas.
By digital twin, do you mean running simulators?
By what?
Digital twin?
Yes, I think for me, digital twin has kind of high fidelity, quasi-interactive, and kind of being able to do some of these scenarios. But I think it's simulators, yes.
So based on your experiences, how close is, for example, if you run simulated cloud data, for example, how close is it to the real data, and how do you, and if there is like a huge difference, domain difference, how do you plan to close the gap, like including domain adaptation, other techniques? So
I think on weather forecasting, and again, we had a workshop, the 3 days workshop, we are pretty close. I mean, if you look at ECMWF, they deploy kind of a machine learning emulator in production. Today I've seen from actually Libby Barnes from Sierra here at CSU, kind of how well actually the I would say what I call data-driven model, the AI model in climate projection actually works compared even to some of our more physical-based models. So I think there's still a lot of work to evaluate, to look at what do they actually learn. But I think there's some ways you can do now science with these emulators in Earth systems, and you don't need to run kind of the more physical-based models necessarily. Still an active, area of research. So I'm not sure if I answered, or if it was more waffling than answering, but we can talk more. So.
Other questions? So I've got another. So what is the utilization right now, the computational resources at NCAR? Is it 100%? Is there?
Not quite 100% because you always have to have gaps, but it's about 90%.
Okay.
So it's pretty high. So.
Okay.
But we still make, every year we make awards available. I mean, we have an allocation process. And again, there's small awards are obviously easier to get, and we have awards for students. So there's capacity.
And just what, if you're looking in your crystal ball, what are you seeing on the federal side? You know, we're seeing proposed impacts at NOAA, and while you do some similar work, it's in a different agency. Are you any more insulated, or are we all just trying to
We
figure
are
things
mainly
out?
funded, I mean, at least in large part, funded by NSF.
You're right.
So that's our main funding source. We've seen some impacts already. We had a radar development, but that project had some other problems that was kind of stopped. I have really no idea. I think one of the dangers for us is we have, in some of our labs, we have climate in our websites, right? So, and we do kind of climate-related research, so that's a threat for us from, but on the other hand, I think maybe if they shut down NOAA research, who is picking up? Maybe nobody, but maybe there's an opportunity for us. I have no idea. I think I think these are chaotic times, sorry. And I think there's a lot of threats, but there might be also some opportunities, and we try to be agile in this space, but it's, I see, unpredictable.
Okay. Anything else? Well, with that, thank you, Thomas. And I think we have a 10-minute break or so. So coming back at nominally 10 after.